بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. So this is the second lecture in chapter 7 about classification. And in the previous lecture we have introduced the concept of classification and the different techniques for classification models. And we started with the logistic regression. And in logistic regression we introduced the concept of the likelihood function and also how to train a model. So if I go back to the previous lecture, we finished by training a simple model by creating a data set composed by features and target variables. We went through the one-hot encoding. We introduced also one-hot encoding. We trained the model. And finally, we got an accuracy value. And the accuracy represents the average performance of that model. So an accuracy of 86%, it means that it's able to classify correctly 86% of the cases. But this is a general value. And yesterday we mentioned that accuracy is not sufficient to evaluate the performance of a model because there are different perspectives that has to be addressed. And in today's lecture, we're going to introduce the different model or the different ways on how to evaluate a classification model. So let's start by this motivating slide. Why the accuracy is not sufficient. Now, after doing the training and analyzing the model, we found that the errors that were made, so there are of two different types. So here we have a binary classification model, whether a person has a heart disease or doesn't have a heart disease. And we find that the model now, true negative, it means that it was able to classify correctly 25% of the cases that doesn't have heart disease. This is what we call true negative. It means true no value. False negative, 4% were classified as having disease and they don't have disease. They are normal person. False negative, it's the opposite. 5 people were identified not to have a disease, and they have a disease. Okay? And here, the true positive, 27% were identified to have a disease, and they do have. Okay? So now, we can say now, it's almost proportional between the misclassification and the correct classification. But we need to analyze this. So we have type 1 error, which is the false positives. Okay, patients incorrectly diagnosed with a heart disease, and the false negative, type 2 error, we have 5 patients with a heart disease that missed the model. And both cases could be dangerous. So imagine that you say to someone that is normal, you have a heart disease. It's not good. And even worse, if someone has the heart disease and say, you are a normal person. And this is why the use of AI is critical in healthcare, because it deals with human lives. But of course, as already mentioned, AI is not here to replace us for decision, but to help us for decision. So at the end, it's the doctor who will take the responsibility to consider whether there is a positive case or a negative case. But of course, because here we have only a small data set maybe, so when we have a huge data set, we can approach something very close to 100%. But still, every AI model is prone to errors. There is no perfection. And based on the concept of true positives, true negatives, false positive, and false negatives, we introduced the concept of confusion matrix. So in this matrix, it will summarize the confusions, the misclassification that occur. And here we have only 2 classes, so it's a 2 by 2 matrix. And the first cell here, it specifies the true negatives, then the false negatives, then the true positive, false positives, and true positives. So what we understand here, we have 25 cases correctly classified as no, 27 cases correctly classified as having a heart disease, and these are the misclassification. Okay. Of course, as already mentioned, the implication of having false positive, you may have unnecessary treatment and potentially emotional distress for the person. And false negative, you will miss the diagnosis and potentially leading to the lack of necessarily medical intervention. Okay, so the accuracy is one of the performance metrics that we consider to evaluate the performance of a classification model. So the accuracy is what? Is the number of correct predictions divided by the total number of all predictions. So what does it mean 86%? It means among all predictions, for example, if I have 100 test cases, 86 were correct and the remaining 14 were incorrect. So this is what we mean. So now we can represent the accuracy using the notation of true positive and true negative. So what we have here in the denominator is the total number of predictions, because the total number of predictions is the true positives, true negative, false positive, false negative. But here for the accuracy, we're going to consider only what is correctly classified. So it's the true positive plus the true negative. This is the number of correct predictions. So that's one perspective in the evaluation of the model. Okay, so it provides an overall measure of the model performance. However, what's the drawback here? It doesn't highlight any impact of the misclassification. Look, I don't have any misclassification here. So it only focuses on the correct classification. This is why we have another metric, which is called precision. What do we mean by something is precise?
As close as possible to the actual value.
Yeah, here it will make a focus on the correctness of positive predictions. Yani it's precise with respect to the positive predictions. Only focuses on positive predictions. So here we have the true positives divided by all the positives. True and negative, positive and true and false positives, yes. So this is the percentage of true positives. The percentage of this is what we call precision. It's precise with respect to the true, with respect to the positive cases. Okay, so this is particularly important in scenarios where the cost of the false positive is high. Okay, for example, in our case, what does it mean false positive? Someone has a disease and we say that is normal. Okay, so if false positive is very critical. Imagine that someone has like a very dangerous disease and say you are normal and spend 1 year, 2 years, and then he can go into very critical case.
He is normal, but they say that he has a disease.
Yeah, he's normal. Yeah, it's the opposite. Yes. Yeah, هي تلخبط هي لأنه yes or no. It's like so. In this particular case, the precision would be important to consider. Okay, so in the case of healthcare, precision ensures that most patients diagnosed positively truly have the disease. Okay, and minimize the risk of unnecessary treatment that could result from false positives. And here, because we have like very close values, we have only two classes, so the accuracy and precision are very close to each other. And high precision indicate fewer false positives. And the high accuracy indicate the overall correctness of the model is good enough. And we have another metric that is called the recall, or also sometimes we call it the sensitivity of the model. It's defined by the true positives divided by the true positives plus false negative. Look here, it's plus false positives. Here it's plus false negatives. And the recall measure the model the ability to detect the actual positive. Sometimes also the ability to remember. Okay? And this is the difference between recall, accuracy, and precision. It's the ability of them to measure the ability of the model to detect all actual positive. So we have true positives, and false negatives. So in heart disease, a recall of 84% means that the model correctly identifies 84% of all actual disease cases.
So a false negative is actually positive?
Yes.
But you misidentified.
It means it's able to recall the positive cases. This is what we call it recall. It's like it reminds what are the positive cases. وفي فروقات بسيطة جدا لكن مختلف تماما. الآن because this data set almost all the values are almost equal. Okay, but we will have some other cases where we can make a distinction between both. Look here, because here we divide by the number of true positives and false negatives. يعني ما معنى false negative؟ يعني in reality it's positive, but it made it negative. So this is why it's counted into the recall. It means this percentage, it was not able to recall that it is positive.
Yes.
Okay? It was not able to recall this percentage that it is a positive case. So it's the ability to remember these positive cases as positive cases. Okay? Yeah. This is why we call it recall. Okay? And also sensitivity. Okay? Both are together, but recall is mostly used here. So the high recall reduces the risk of missing a diagnosis, missing that a positive case is really a positive case. Now, which metric is better than the other one? Yeah, it's a bit confusing to select one of these ones. You can say that they are equally important. You can say that probably one is better than the other. What would be the solution here?
If I would guess, I guess here, in this case, recall is more important because you want to identify the positives.
Yes, at the end it depends from which perspective you see it. So it will be subject to interpretation.
Human lives.
Yeah, now to merge all these metrics, we define a metric that is called the F1 score, which is basically the harmonic mean of precision and recall. So it will combine both precision and recall to balance between these two metrics. And this is like the standard metric for, let's say, the performance of the model. It's like a summary. It's like a summary. Of course, usually when we interpret a model, we need to take into consideration all these different perspectives with respect to the real life application scenario. But the F1 score, it provides a better balance that combines both the precision and the recall equally, and is defined by 2 multiplied precision multiplied by the recall divided by the sum of the precision and the recall. And in our case, in the F1 score in the healthcare, with a value of 84% in the heart disease diagnosis, this metric indicates a strong balance between precision and recall because it's high. Okay? Essential for effective and efficient patient care. It ensures that the model is not only accurate, but also make a balanced in terms of avoiding unnecessary treatments and not missing critical diagnosis. So how to do this in Python? Now these are the concepts. There are methods in Python that allows you to extract these metrics after you finish the training of the model. So yesterday we did the training of the model and we get the accuracy. But now using the same model, you can actually extract all these values. So first remember that we use the model to derive the Y prediction, okay, the predicted outputs. So in scikit-learn, we have here scikit-learn.metrics, which provide you the confusion matrix, the accuracy score, the precision score, the recall score, the F1 score, classification report. We'll see all of these ones. So just to get the accuracy, you call the function accuracy score. You provide the grounded truth, which is the test output, and the predicted output. And it will calculate the accuracy. It will also calculate the precision, and with respect what is the positive label. So you can specify what is the positive label if you want to calculate the precision. The recall score, and the F1 score. So all of these, you can get them, and this will be the result. If you want to get all of these metrics in just one line, so we use the method classification report. So classification report, it will provide you this table. Okay? So report equal classification report, you provide the target output, the predicted output, and also the name of the classes, model.classes. Okay, because here we have 2 classes, so it will provide you the confusion matrix with respect to all classes. And you can also calculate the confusion matrix, yes.
In neural networks, would we do this for each individual node?
No,
Only at the end result?
at the end of the result, yes. If you have a neural network, you train it completely, you will have a model, you calculate your predictions, and you have your ground truth output. Usually you calculate the difference between the output and the output in different ways. Okay? True positives, true negatives, and so on.
We don't care about these metrics during training. Only care
Yes,
about-
this is during inference,
No.
at the inference time. Why? When you do the training, you want to, for example, you are a company, you want to sell your model. Before selling your model, you need to make extensive testing.
That's correct.
Yes, you need to understand the limitation of your model. And this is why you need to do all these kind of extensive testing reports to understand what is the issues, whether these issues are acceptable, not acceptable, okay? Because any AI will solve a problem, so you want to know, and any AI model will have limitations. You need to understand the limitation of your model. There is no perfect model. Absolutely, there is no 100% model. Even if it looks 100%, it may fail at any time. You don't know when, okay? Example of Tesla, you know, they made self-driving cars and they crash. You don't know when they crash. Sometimes they may confuse a car for an animal or a pedestrian for traffic light, you know. Now, there was a funny video, you know, one pedestrian just wear here like a stop sign and in the US and just stop on the street. So when a Tesla came, just it stopped in the middle of the street because it has seen the stop sign that what is wear by a person. Yeah, that's kind of a threat of this kind of AI models. Yeah.
But isn't it useful for during testing
Mhm.
to know exactly where to focus on? Let's say the accuracy is low, we can divert it so that we punish more if it's inaccurate, if the precision is off.
Yeah, of course. Usually when we do that and the model is not satisfactory, we need to take other actions.
Go back.
Maybe adding data set, maybe changing the model, you know. Yeah. But the most important thing is that we need to understand all these different metrics, okay, and also make a good interpretation. So we can also calculate the confusion matrix using CM, using confusion matrix method, takes also the test, the prediction. And this code, this is the code that prints this heat map. Okay, so the heat map is a very good way on how to visualize the correct classifications and misclassification. And this can be applied to any number of classes. Okay. Okay, classification report, that's fine. Now, after extracting these results, okay, we didn't stop here. This is where the real work started. We need to interpret these results and get insights. Now, if I give you these results now, what are the main interpretations? This is for the heart disease problem. Imagine now you want to sell it to a hospital and say, okay, interpret me these results. This is the work of a data scientist. Now we did the programming part, and the most important part is how can I make use of this? Yes, how can I make use of these results? Okay, now interpret these. First of all, start by interpreting these values.
We can see that
The model predicted 83% of the individuals do not have heart disease and 84% of the individuals have heart disease.
Yes.
Though it has some fluctuations, we can
Yes,
enhance, we can make it more accurate with some certain parameters in the model.
yes. And also, we can observe that there is no bias between the no and the yes. I mean, all the performance metrics are almost equal for all of them. So the data set is kind of balanced, and we have like a fair distribution between the classification and misclassification between yes and no classes. And this is important in observation because sometimes you can have 90% accuracy, but one of the classes have only 50% accuracy and the other could have 99% and so on. So this kind of big discrepancies in the class performance, that could be a very big issue, especially when you have unbalanced data set. What does it mean, imbalanced data set? It means one of the classes has more values than the other, has more records than the other. In this case, we can have a misclassification for one class more than the other. But here it's like a uniform distribution between both. I mean, we don't have too much discrepancies. Okay, so this is how we can interpret. First of all, we describe the results. We can make a descriptive analytics. Okay, we can say, like, as you already mentioned, we have 83% of the prediction for non-disease cases were correct, and 84% of the prediction for disease cases were correct. For the recall, okay, 83% of actual non-disease cases were, yeah, for all of these correct non-disease cases, 83 were identified. It's not among all of these, only from the actual non-disease case, and this one of actual disease cases. Yes or no. This is the recall. It's the ability to recall the correct cases and the incorrect cases. Now, they have different formulas, but they just have the same numbers. But this is not the case usually in real classification problem. Maybe this data set was very well balanced. And the F1 score, of course, it's the average of both. So basically, it's the same.
Doctor?
Yeah.
What, in your past experience, what score did you get that aided your interpretation?
Well, the first score usually that we look at is the accuracy, before stopping the model training. But after the accuracy, this is where we start working on the things, For example, a couple of years ago, we trained the model to classify cars brands, whether it's, for example, Ford or BMW or whatever. Okay, and we have like 40,000 images and 200 classes. So we've been doing all these kind of works to see, for example, whether one class of cars has less accuracy than the other. So we need actually we collected this confusion matrix to understand where the errors are. So we do pretty much the same thing. We don't rely on only one metric. We have a global view of all these different type of metrics to extract insights, technical insights, and then plan optimization strategies. Okay, this is the way on how we manage. For example, here, one of the technical insights, okay, starting by model evaluation metrics review, we can observe that both the weighted average and the macro averages for each of the values is at 84%, reflecting a homogeneous accuracy across different classes. We don't have an imbalanced or a bias toward one class as compared to the other. We have a metric uniformity. Okay, all the values, precision, recall, F1 score, are equally strong. Okay, so this gives like a uniform quality among all these different classes. But of course, maybe 84% by itself could be not acceptable in the healthcare sector. Okay, but now if we don't accept this one, we need to maybe make the data augmentation or make other measures in order to improve to 90%, 95%, and so on. Okay, strategic enhancement priorities, for example, to optimize the sensitivity or also the recall. Despite the high score, enhancing the recall is paramount to ensure no critical condition goes undetected. Okay, so here it means we need to do some improvement in order to recall the positive cases. Because if you don't recall the positive cases, you may have some people with a disease that will not be detected. And this could be life-threatening. Okay, now we will give priorities on how we want to optimize. And this is a context specific. Okay, we can do algorithm refining. For example, some of the ways we can do ensemble methods. I can have different models, and every model will give me a prediction. Then I will make a vote. Imagine that I have 5 models. 3 give me yes, and 2 give me no. So I will make a voting, and will say, okay, this is likely a yes. This is called ensemble classification models. We did this, we have a paper on COVID-19 where we did ensemble classification, and we can increase the performance from, for example, 92% to 98% to 99%. I will send you some of this paper and you will see, you will understand a lot of things, although it was done in computer vision, but you will have the ability to understand the experiments and the results and get different insights among them. Okay. Now, is this sufficient? Imagine, look now, when we did this classification report, inherently, we have a sigmoid function, okay? Because what we have? We have features, which are the medical condition of the person. We will use a classifier, the logistic regression. And finally, I will have a probability here. Then, based on the probability that I will get, I will say whether this is yes or no. So if I have 55% yes, what will be the result? It will be yes. Why?
It's above 0.5.
Yeah, so here, inherently, you have 0.5 as the decision threshold. But is this the best threshold? That's another question. If I change this threshold, so this is why there is a limitation of just using the precision and recall, because they are based on specific decision threshold. They do not provide insight into classification performance across varying thresholds. So if I change the threshold, would I get a better performance? What's the ability that the model is able to differentiate between a yes case and a no case? And also, they are not very good for unbalanced data sets. Now, our model we should have made an exploratory data analysis, and we could have observed that the yes is probably equal to the no. So we have kind of balanced data set. Having a balanced data set, that's one of the most critical issues. But sometimes in reality, you can't. Okay, maybe some data is more available than other data. Okay, if you want to train, for example, a model on COVID-19, maybe you don't have too much X-rays on COVID-19, for example. So you may reduce your data set or work with imbalanced data set. So sometimes you are in a situation you have to decide on how to go. Because when you have an unbalanced data set, this matrix will be biased toward the majority class. If you have a class if we have, for example, 80% of yes and only 20% of no, very likely it's going to bias the model. Okay, because most of the time it's going to say yes, 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 yes. So at the end, it tends to say yes in most of the cases. Okay, so the data set itself is very important to make sure that it's balanced and doesn't have any issues. And now let's assume that it is balanced. We need to analyze, okay, what will be the better threshold. Look now, for example, if we change, now I've made an experiment, I changed this threshold from 0.5 to 0.2, and I have an accuracy of 0.79 instead of 0.48. But I have a recall of 0.91. Explain me why the recall is better here.
Because of correctly identifying more yes values.
Yes, the correct, I will say yes whenever I have something above 0.2. And most of the time, okay, so I will remind most of the cases, but I will make more mistakes. So I will look at the precision is becoming lower because many cases that are not with heart disease, I classify them with heart disease. Okay, look now, the recall is higher, the precision is lower, the accuracy is kind of in the average. Okay, so now it's important to analyze these metrics with respect to different thresholds. What will be the curve if I change these different thresholds? And look now, even the confusion matrix, instead of 25, I have 19, but here I detected successively 2 additional positive cases. But I misclassified 6 more negative cases. So there is a trade-off to do here. And this is why we have a recourse to what we call the ROC analysis, which is the recipient over the curve. Okay, so here we have a curve. So what do we do? We're going to have the true positive rate. We calculate the true positive rate, which is in the y-axis. It's called by TP divided by TP by plus Fn, which is the sensitivity of the recall. So this is the recall. And the false positive rate which is 1 minus specificity. This is 1 minus the precision. And for each threshold, I'm going to plot a point. And there I will have a curve over here. So I've put you the algorithm here. We're going to start by threshold equal to 1. And for each threshold, we calculate this value. I calculate this value. And then, we compute all true positive and true negative. And then this is a point for that threshold. And finally, I'm going to plot all these points and connect them with the lines. And this represents the receiver operating characteristic curve. So how to interpret this? This is the diagonal. So this represents 50%, 50%. It's like here you have a random guess. Okay? So if you have a curve that is overlapping with this diagonal line, it means that the model is not able to differentiate anything. It's completely random. Okay? It is completely random model. Okay. And if the model is higher than this curve, it means it has a good ability to discern what are the positive cases and the negative cases. Okay, so above the diagonal, it indicates better than random performance. The higher and closer to the top left corner, the better the model sensitivity and specificity. Why? Look now. This is true positive rate. Okay, let me take a point here. And false positive rate. Look, if I go in that direction, what I'm doing? I am increasing the false positives. So I am deteriorating the model. Look now. If you increase the false positive rate, the increase in the true positive rate is higher for a particular threshold. Okay? So this means that the model is less sensitive to the errors. Okay? So in general now, if we have a curve that is closer to the top left, the closer it is, the higher the performance of the model will be. So we look at the shape and direction. A steep initial ascent suggests a high sensitivity. Okay, this is steep, but sometimes it could be steeper. If I have something sharp like this and sharp, it means a perfect model. But in reality, we cannot have. So the steepest, okay, the steeper, the better the curve is.
Doctor, here we're plotting this according to the true positives.
Hmm?
Is that we're doing this according to the true positive rate.
Yes.
That means that we will deteriorate in the false Tani.
Yeah, but here we look at the proportion. Okay, if you deteriorate a little bit, so the increase of sensitivity is higher. The increase in the rate of sensitivity is higher. Okay, imagine that you have something opposite. You increase and you have the same sensitivity. Okay, and then so that's not perfect. And look now, we also calculate what we call the area under the curve. So what is the total area here? What is the total area? I have here from 0 to 1 and here from 0 to 1. What is the total area? 1 multiplied by 1 is equal 1. If you have an area under the curve, so look, the area that is under the curve means this part is 0.91. It's close to 1. So this is an indicator. When it is close to 1, if it is 1, it's perfect discrimination between positive and negative. If it is close to 0 or close to 0.5, it means no discrimination. It's random. If it is below, it's worse than random. Okay? So the area under the curve here, 0.91, it gives you an indication about the performance of the model across different thresholds. Okay? Now the difference between these simple metrics, it's only one threshold, it's 0.5. But this is more general.
How can this be negative?
Huh?
How can this value be negative?
No, it's an area. An area cannot be negative. Yeah. Okay, so if you want to have a better analysis of your model, you will have a recourse to the area under the curve and the receiver operating characteristic, the ROC curve. These.
So how do you know which threshold is the best?
Hmm?
Which threshold is the best for our model?
Which threshold? Now it depends on how you will define it, whether you will focus on the accuracy, on the precision, on the recall. Because when you change the threshold, look, the recall has increased, the precision has decreased. So we need to find something. Now, the objective is not to find the highest one, but it's to look at the overall performance of the system regardless of the threshold. You see what I mean? Okay, so here we have the model gives like around 91% of robustness of the model. Okay, this is how we evaluate it. Yeah, now this is like the standard approach